Welcome to the first law of thermodynamics, and in this video we're going to be looking at example 2, but before I jump into that, maybe I'll do a little bit of discussion about the first law of thermodynamics. So really, actually, to start off, I should state that the first law of thermodynamics is really just a law of conservation of energy. But if you recall, the energy of the system, which we call like the internal energy, U, depends on really, well, the position and the motion of the particles in the gas. But if we're discussing explicitly an ideal monatomic gas, that internal energy is given by 3/2 N, the number of moles, R, the gas constant, and the temperature in Kelvin. So, of course, if the temperature of the gas increases, then the molecular motion of the molecules increases, and you've got a greater internal energy, and vice versa. So, yeah, we can tell whether the internal energy of the gas is increasing or decreasing by really just looking at this equation. But how does that energy increase or decrease? Well, really, there's basically two ways. You could either heat the system or you could do work on the system, right? So heat, if you recall, is really the transfer of thermal energy between the gas and the surroundings by the means of conduction, convection, radiation, which is the last unit that we talked about. And that occurs when there's a temperature difference between what's inside the gas and what's outside. So if, let's say, the gas was hot inside and outside was cold, then thermal energy would flow from hot to cold. All right. The other way energy can be converted or the internal energy of a gas can increase would be if there is work being done on the gas or work being done by the gas. So maybe we should have a little quick discussion about the signs. If the sign is positive or whether it's negative. Well, the discussion about heat, well, that's pretty straightforward. If the heat goes into the system, then that's positive. And if you flow out, well, that's negative. I think that's relatively straightforward. The one that's a little bit trickier, because I think there's various definitions for the this first law of thermodynamics. Some people use delta U equals Q minus W. We'll be using the one delta U equals Q plus W. And we are interpreting it based on the gas. So imagine if I wanted to increase the internal energy of a gas, I would want to compress that gas, and then I would increase its internal energy. And that compressing of the gas would be considered positive work being done. So if you do work on the gas and you compress it, that's positive. If the gas does work on the surroundings, it pushes outwards, volume expands, then that work is negative. Okay, so positive work done when the gas is compressed, negative work being done when the gas expands. Okay, and that internal energy change comes from the sum of these two. Now on to example number 2. So we have a gas that absorbs 5,000 joules of energy while doing 2,000 joules of work on the environment, and we're asked to calculate the change in internal energy of the gas. Okay, so we'll start off by writing what we know. We are given that it has 5,000 joules of energy that is being transferred into the gas because that's absorbed. So that's what we call heat. And we're putting that as positive because it's flowing into the system. Then at the same time, we have 2,000 joules of work that is being done on the environment. That means the gas has to be expanding if it's doing work on the surroundings. So this work is this is negative work being done. And we are trying to find, I guess in part A, the change in internal energy. Okay, so we're going to apply the change internal energy, the first law of thermodynamics, delta U equals Q plus W. So delta U would be equal to 5,000 joules of thermal energy that flowed in, plus negative 2,000 joules of work being done. So this gives you a change of internal energy of 3,000 joules. Okay, so even though 5,000 joules flowed into the system by heating, the gas was allowed to expand and 2,000 joules flowed out. And so the net energy that the gas gains is just simply 3,000 joules of energy. Okay, so now we'll go on to the next part, and we are looking at the internal energy now drops by 4,500. And at the same time, 7,500 joules of energy is expelled out of the system. We are now told that it's going through a constant pressure process, and we need to find that change in volume. Okay, so we'll write down again what we know. So our given. So we are told that the internal energy drops by 4,500 joules of energy. And then this 7,500 joules of energy is energy that is expelled out of the system. So this is actually heat, and it's expelled, so it's leaving the system. Okay, and we're asked to find here the change in volume. Call that part B. So this is actually a two-part stage, if you look at it. In order to find the change in volume, we need to figure out what the work done is, because if you recall earlier, work is equal to negative P times delta V. So I won't be able to find the pressure until I find the work being done. So that's why this first information is given. So we're going to apply the first law of thermodynamics, delta U equals Q plus W. We've got negative 4,500 joules, and we have negative 7,500 joules of heat, and then that's equal plus work. All right, so then that gives us a work being done of, well, the difference between 7,500 and 4,500 is 3,000 joules. Okay, so now what we do is we apply the equation for work being done, assuming that it's constant pressure, which is equal to negative P times delta V. So if we have 3,000 joules of work being done, and the pressure is 1.01 to the power of 5 pascals, and then we have our change in volume. So dividing here, 3,000 by 1.01 to the power of 5 gets us negative 0.0297 meters cubed. Okay, and that's it for this example.